All right, let's look at integrating powers on secants and tangents. So if the power over secant is even and positive, we're going to want to take a secant squared x and factor it with the du. We're going to convert all of our remaining factors to tangent using your Pythagorean identity, and your u will equal tangent of x. If my tangent is to an odd and positive power, then we want to save one tangent and one secant factor for the derivative du. We're going to change everything into secants, and we're going to let u equal secant of x. So remember, the derivative of secant of x is secant x tangent x. Derivative tangent of x is secant squared x. If there are no secant factors and the power on the tangent is even and positive, we're going to convert a tangent squared x factor to a secant squared x factor by the Pythagorean theorem, one of those identities. If you have secant raised to a power and is odd and positive, then we're going to use integration by parts. If none of these factors we can fit 1 through 4 work, then we're going to convert everything to sines and cosines and can use our powers on sines and cosines. So as I said earlier, the derivative tangent of x is secant squared x, and the derivative secant x is secant x tangent x. If I integrate tangent of x, that's the natural log of secant x plus c. And if I integrate secant of x, that's the natural log of secant x plus tangent of x plus c. And our Pythagorean identities, tangent squared x plus 1 equals secant squared x. That's where we'll take one of your tangent squareds, use this identity here, and change one tangent squared x to a secant squared x minus 1. All right, examples. Example 6, tangent cubed x secant squared x dx. So here you have secant squared x. We're going to save that. We're going to put it with our dx, so that's my du, which makes our u be tangent of x. And this is just a perfect straight u substitution. So that's going to give me the integral of u cubed du, which is u to the 4th over 4, or 1/4 times u to the 4th plus c. And then bring your tangent of x back in for u, and we're done. Now, same problem, okay, just a different approach, because you also have tangent being odd. You could also, probably not recommended, but it would still work. You could have, okay, let's take one tangent and one secant and put it with du, for our du, so with the dx. So that's going to leave me u being secant of x. So I separate tangent cubed x to tangent squared x times just one secant of x. Here's the 2 I factored out to match up with my dx. All right, use your Pythagorean identity to change tangent squared x into secant squared x minus 1, and now do your u substitution. So u squared minus 1 times u du. Distribute the u, integrate by the power rule, u to the 4th over 4 minus u squared over 2, or multiply fractions to the front. Substitute your secant back in for the u, and there's my answer. Looks completely different than this, however, they are both the same answers. So I went to my calculator and I graphed this into y1, and then I graphed this into y2. So this is my blue graph, this is my red graph, and as you can see, they're the same size and shape, just one shift lower or one shift above the other. So then the next thing I did is I took in my table, y3, I made that y1 this function minus y2 this function, and if you look at my table, all the points differ by 0.25. So if this was my blue curve, if my constant was minus 0.25, it would match this curve. If I put in a plus 0.25, it would match that function. All right, example 8. Here we have secant to the 4th of 3x, tangent cubed to 3x. Again, both rules work. Just come up with the easiest amount of work. They're about the same. I personally would let the u equal the tangent of 3x and take secant squared 3x and put it with my du. So the derivative of tangent 3x is secant squared 3x. But remember your chain rule, when you take the derivative of the inside, 3x is 3, you have to multiply it to the outer function. So we'll solve this to get our secant squared 3x dx by itself, so I'll have to divide over the 3 because I have no scalar factors of 3. So here I'm going to isolate the secant squared 3x with the dx, and then change this secant squared 3x using my Pythagorean identity, so to get everybody into tangent of 3x. So tangent squared 3x plus 1 times tangent cubed 3x. Now we'll substitute in 1/3, move that to the front of the integral. Here's my du, here will be u cubed, here will be u squared plus 1, distribute, integrate, that will give me 1/3 times u to the 6th over 6, or multiply by fraction 1/6, plus u to the 4th over 4, or multiply by 1/4, whichever you prefer to do is fine by me. Distribute in the 1/3 and substitute the tangent of 3x back in for u, and there's my final answer. Example 9, tangent squared x over secant to the 5th of x dx. We don't have any rules here. Remember we had, oops, let me go back, I wanted to go back, secants to the even power, tangents to the odd power. But here, tangent to an even, secant to an odd, you have to convert everybody to sines and cosines. So I'm going to look at this as tangent squared x times 1 over secant x to the 5th power. Tangent squared x is sine squared x over cosine squared x. 1 over secant, the reciprocal of that, is cosine, so times cosine of x to the 5th power. We can cancel some cosines, and now we can integrate using the rules for our sines and cosines. So cosine is to the 3rd power, so we're going to take one cosine, move it with our dx, and then we'll change our u will be sine of x, our du will be cosine x dx. Change cosine squared of x to 1 minus sine squared x. Now there's my du. Put u's in for all the sine x's. U squared times 1 minus u squared du. Distribute. Integrate by the power rule. U to the 3rd over 3, or times a 3rd. U to the 5th over 5, or times 1/5. Bring your sine of x back in for the u's, and there's my final answer. Again, just don't forget your plus c. Example 10, here we have integrating tangent of cubed x dx. There's no secants in the problem, so what I need to do is just break this apart to to a tangent squared x times a tangent x dx. So there I separated it, substituted it in, and distribute the tangent. Now, what this is going to do for me is I'm going to rewrite this as 2 separate integrals, because if you look on your table of integration, let me throw it over here real quick, you can integrate tangent of x, that's number 12, so we can integrate that one from the table. And now we'll take the first part and we'll do our powers rule on secant squared. It's an even power, so we'll save that with the dx. U is your tangent of x, that's a straight u substitution. Integrate both of these, so that'll be u squared over 2 minus the natural log of the absolute value of secant x plus c. Put your tangent x back in for the u. 1/2 tangent squared x minus the natural log of secant x plus c. Oh. All right, those are absolute value bars. I'm not sure if I said it or not. So yes, minus the natural log of the absolute value secant of x. Example 11. Now we're going to do some integration with lower bounds and upper bounds, so we have some definite integrals. So again, cotangent squared x, there's no secant here. Change this to secant squared x minus 1. The reason I want to do that is I can integrate this. On your table, secant squared x is number 8. That's going to integrate to just a tangent of x. We integrate the 1, 2, and x, and then we evaluate it. We'll substitute in our pi over 3, then substitute in the zeros, and we'll subtract these two. Pi over 3 is 60 degrees. So if you wanted to make a right triangle, opposite of your 60 degrees is radical 3 over your adjacent, which would be opposite your 30 degrees, is a 1. So this is the square root of 3 minus pi over 3. Tangent of 0 is 0. So final answer is square root of 3 minus pi over 3, or if they want a decimal answer, 0.6848. All right, almost finishing this up. Go back in your notes to when we filled this all in. Because what I want to do with this part of your notes is make cosecant cotangent rules. So in your notes, choose a different colored pen, something here. In every place you see the word secant, you put cosecant. And everywhere you see tangent, you put cotangent. Okay, so this secant squared becomes cosecant squared. This tangent becomes cotangent. This u equals tangent x is u equals cotangent of x. Number 2, tangent of x to cotangent of x. All right, secant goes to cosecant, tangent goes to cotangent. Secant to cosecant, secant to cosecant. Number 3, if there's no cosecants factors, and your cotangent is to an even and positive power, then tangent squared x will be cotangent squared x. Secant squared x is changed to cosecant squared x, and you'll factor by your Pythagorean theorem identities. All right, and secant raised to the m power, where m is odd, change that to cosecant to the m power. You'll use integration by parts. If none of the above work, you still change everything to sines and cosines. All right, tangent of x is cotangent of x, but make a special note, its derivative is negative cosecant squared of x. Secant x, make that cosecant x, but its derivative is negative cosecant x cotangent of x. Integrating cotangent of x is the natural log of sine of x. Natural log of the absolute value is sine of x plus c. Change secant to cosecant, then it's secant x minus cotangent of x inside your absolute value bars of your natural log. Tangent squared, cotangent squared. Secant squared, cosecant squared. Same as here. And you just created the rules for cosecant and cotangent. Now, if they give you a product to sums identity to use, I guarantee you I will provide this on the test if I wanted to do that. So I'll give you these properties. So here, if you multiply sine and cosine where your arguments are different, we want to rewrite it like this. Simplify the insides, integrate. All right, so we're looking at cosine A, cosine B. So A is 2x. B is 6x, so this will be cosine of 2x minus 6x, 2x plus 6x. All right, so combine that together makes cosine of negative 4x plus cosine 8x. We'll integrate this. Now, it's important to know that cosine and secant, the reciprocal of cosine, is an even function. So if you have a negative argument, you can change it back to a positive. It flips over the y-axis. You would get the same y value if you did a cosine of a positive x and cosine of negative x. So I changed it. We'll integrate it. Integrating cosine of 4x is sine of 4x. Derivative of 4x is 4. I divide that into my sine of 4x or multiply by a fourth. Cosine of 8x, sine of 8x, derivative of 8x is 8. Divide by 8 or multiply by 8, multiply in the halves, and there's my answer.